Right, so alcohols ABCD are structural isomers of each other having the molecular formula C5H12O. And they have given a specific information. ABC shows optical isomerism. I think the best way to go through this is in the board. So I'll discuss this on the board. So we have given a formula that is C5H12O. And this contains A, B, C, D. So 4 different structural isomers as far as they have given in the question. And they have say, we have another additional information. ABC shows optical isomerism. We should give this is not optically active. Right, this is not optically active. So this is not an optical active compound. D is not an optical active compound. So draw possible structures for ABC. So they haven't given any other additional information about ABC. So we need to use this particular chemical formula that is given and try to draw 3 different structures which are optically active. So we will go through the simplest one. So this is an alcohol. So I'm going to write down OH that is added to 1 carbon unit. And we are remaining with 4 carbons. So I can add CH2, CH3. So 3, 4, 5. So 4, 5 is not okay. So if I draw here CH2, CH3 and another carbon 1, 2, 3, 4, 5. So I have to put this one as hydrogen. So now this is not an optically active compound. Why? Because there are 2 CH2, 2H3. So this is a problem, right? So this can be the structure of B because that is not optically active. So let's think that maybe B. Maybe B. We don't know, right? Then, but if I put this CH2's one of the CH3 groups here, then there is OH here, there is hydrogen here, and this becomes CH3 now, and this one of the CH2 groups goes here, right? Now you can see 4 different groups are here, which gives you the idea now this is optically active, right? This is one. The other thing is, instead of having a CH3, CH2, CH3 here, I can put this one of this OH here and this CH3 here, right? So the other idea is just manipulating the same structure, right? So instead of having this OH directly bound, I'm going to put this one as CH2OH, right? Then this is same. And this is going to be CH2, CH3 the same, but here one CH3 is here. So to get this structure, I put one here. To get this one, I put one here. That is one. So this is also 4 different groups. So this is also going to show optical activity. So these are chiral carbons, and we have to find another structure which provides me. This chain can be branched, right? Because this is attached like this. So instead of attaching here, I can attach from here, right? So this compound would be OH, hydrogen, CH3, attached from the middle. So there will be 2 CH3. So these 2 are CH3 then. And there will be 1 hydrogen here. Right? So this is also an optically active compound. So this is the chiral center. So these all structures are possible here. This one, this one, this one, and this one. Okay. The first question says draw possible structures for ABC. So you can write down these three in three boxes. You don't have to mention A is this, B is this, because you don't know. So this can be A, this can be A, this can be. Just write down these three structures in the three boxes. That's it. Okay, so we will move on. So you can draw these three structures. That is why they have given three boxes. Then we have a separate piece of information, and we think this can be D because when the chain is considered to draw a possible structural isomer, this is the only possible way to draw a structural isomer based on the fact this is optically inactive, because D is optically inactive. Don't forget that. When BCD are reacted with acidic K2Cr2O7, so this is, you know, this is an oxidizing agent. So don't forget, this is oxidizing agent. X, Y, Z are formed. So one of these two structures, B and C, and our assumption giving D is reacting with K2Cr2O7. So we will check first whether this can be reacted with K2Cr2O7, right? So this can be reacted with K2Cr2O7 because if you do the reaction here with K2Cr2O7, the oxidation, what is happening here? This will form the hydrogen is going to be removed. So this one will form CH2, CH3 and CH2, CH3, right? So if I draw that correctly, so CH2, CH3. This structure is formed. And when you do this one with K2Cr2O7, I will come to this one. Okay. So we will, I will stop sharing the screen and I will show the board here. So when you do this one with K2Cr2O7, it will form the ketone. And here, when you do it, this one also will form the ketone, COO, but here this is CH3, and here CH2, CH2, and CH3. This is the other one. And this is the other one with K2Cr2. This will form again the same ketone, CH3, but here this is the linear chain, and here this is the branched. So this all ABCD all gets react with this K2Cr2O7, but don't forget we are still not confirmed whether this is K or not. Okay, so don't forget that. Then we will read out what is actually happening in this. Because A, B, C, all three react with K2Cr2O7. So we have A, B, C. But here in the statement, they say B, C, D are reacted with acidic K2Cr2O7 and form X, Y, Z respectively. The products X, Y, Z can be converted back to B, C, D respectively by using NaBH4. So don't forget this reactant. So we forget about this one. This one also reacts with that and forms the CH3, CH2, CH3 hydrogen. But this is a primary alcohol here. When you add K2Cr2O7, first it will go towards the aldehyde, and finally it will be oxidized towards to carboxylic acid. Right? So don't forget about that. And they say by using sodium borohydrate, NaBH4, these oxidized compounds can be returned back to its same form. Okay, can be returned back to same form, except only one in this entire structures, because this can be done using NaBH4 because this is a ketone. This is also possible. This is also possible, but this conversion from carboxylic acid to the relevant same primary alcohol using NaBH4 is not possible. Because if you can remember about our theory, we always say if you have a carboxylic or an ester group OCH3, COCH3, methoxy group. If you want to reduce this to CH2OH primary alcohol like this, you have to use lithium aluminium hydride. Sodium borohydride cannot do this. So according to this piece of information, the question that they asked is, what is the real structure of A now? So you can understand BCD can be returned back. So these three structures can be returned back to its original state using sodium borohydride. So this is simple A, simple A. This is also possible, this is also possible. So this is the only point where you cannot do this. So what is the real structure of A? Because A is not going to perform that. So this is the real structure of A. Because when you add K2Cr2O7, A to A1, A will be oxidized to carboxylic acid, but it cannot return, right? So that's the idea. Because these BCD all can come back. So this is also done. On heating with conc H2SO4, A and B gave E and F respectively, while C and D gave the same product G. So we have to find C and D that react with conc H2SO4 to give the same product G. So what is the compound that gives the same product G? Okay. That's the thing that we have to find based on this question, right? Because we know now this is our A. This is A, alcohol. Okay. And this is our D. If we think that, and A, D, and those two are correct, so we should be remaining with B and C, which can be either this one or this one. Okay, but don't forget A and B gives E and F. So A and B gives E and F. That is one thing. And C and D gives same compound with conc H2SO4. Remember the term conc H2SO4. So we have to find the reaction with conc H2SO4, right? So let's see what are the reaction that is going to happen. So I am going to remove the reaction with K2Cr2O7 now. So these are not going to happen here now. Right, so A and B going to give E and F, C and D going to give G. So when you do the conc H2SO4 reaction, so what is going to happen? Dehydration. So this OH is going to remove with the adjacent hydrogen, where the carbon which contains the lowest hydrogen. So here the adjacent carbon for this one is this and this. But here there are 3 hydrogen, here 2 hydrogen. So this compound is like this. Okay, this is this. And for this one, it is the adjacent carbon is these 2. But don't forget here only 1 hydrogen. So this compound is this. Okay, and this one CH2OH, the adjacent carbon for this hydroxyl is this one, only there is only this one. So this will be giving 2 hydrogens since this particular carbon, and this carbon is going to attach with CH3, and this is going to attach with CH2, CH3. So what are the remaining? So here it is this one. with this one. So this one would give carbon, hydrogen, CH3, double bond, and another one with hydrogen and CH3, right? Is that okay? OH is going out, so hydrogen, and here this is CH2, CH3. Don't forget that. This part, this OH with this hydrogen, so CH2, CH3 carbon, CH2, CH3. With then CH, so this is carbon with one hydrogen and one CH3. So these are the possible structures, right? So according to that, you see here, this structure and this structure is same, right? If you can understand what I have written clearly, the structure that D, the expected D that is going to give this with conc H2SO4, and the structure this is going to give this, and these two structures are same. The only difference is CH3 I have drawn here on top, but here it is bottom. So these two structures are same. So which gives the idea this compound G is this. Either this or this, you can imagine. And C and D, D I have already mentioned, this could be D. So this is our C. And this is A, so A gives E, and my B gives F. Okay, so this is the way that you can approach this question, right? So first we draw for three structures of ABC, then we possibly draw the only available minimum option that gives the optical inactivity. Then by using potassium dichromate, we found the original structure of A. And then finally, we used the conc H2SO4 to find the original structure of C and D. So when you find all this, then you have found all the structures, right? So that is the possible way to understand. So you have you know the real structure of A now. Then you know B, C, D, E, F, and what is H here? So we have to check H as well. So E and F are reacted with HBr to give the same product H. So what is E and F? So typically it's this one and this one, right? So when you try to analyze the reaction of these two, right? So this one with HBr and this one with HBr is giving H. So let's check. So HBr, so you have to add H here because this is the carbon with highest number of hydrogen according to Markovnikov rule. So this part will be converted to CH3, and this there will be bromine here in this particular carbon, and there will be CH3 here, and there will be CH2, CH3, right? And this one again, when you add HBr here, there is one hydrogen here, so there should be a hydrogen here and Br here. So basically, this is also like CH3. Then here there will be CH2, and this carbon will have the bromine and CH3, and this is the same structure, right? CH3. So these two are same. The CH2, CH3 is here, two CH3 groups is here, and bromine is here. So these two are same structures, okay? But don't ask this CH3 is this here and this here. This is a single carbon, it can rotate around its bond angle. So these two are same, and this is H. That is what finally they have asked in the question. Okay, so this question is not hard, but you have to organize this question to arrange it in a particular order. Otherwise, you will be lost. Okay, so this is a very nice question, organic question, I would say. So you know all the structures. And draw the structures of the diastereomers of G. So we know G, there was CH2, CH3, and CH3. So you can draw the cis-trans configuration of G. Okay, it is very simple. Right, so we are moving to part B of this particular question. So consider the two reaction schemes given below. So NH2, CH2, NH2. So you know when you add Na2HCl at 0 to 5 degrees Celsius, so this part is going to form the typical compound, which is normally it is N2Cl. That's the main part that you necessarily need to mention. But don't forget, this is electrophilic substitution that is happening when the reaction is happening with phenol. So we are familiar with this one. So this could normally form the substitution. And there is phenol with this OH. So here there is this hydrogen, which is a little bit of electrophilic in nature. So here this N2, don't write into Cl, write N2 negative. So it will be nice, right? So since this is electrophilic, then this is removed, right? So this is typically a electrophilic substitution reaction, right? So there will be this N2 part that is attached to this para position of this phenol. Okay. Reaction 2, so B, to convert from the Cl to OH, you can add NaOH. So that is very simple. And this is a nucleophilic substitution, right? And from this to this, you can add PCC, pyridinium chlorochromate, because this primary alcohol is stopped at aldehyde. And then you add HCN. So this is now going to be a nucleophilic addition, right? So this is AN reaction. So here there will be these OH. This carbonyl carbon can be converted to OH, and there is this hydrogen that is in this carbon, and this HCN is added. So cyanide is added. So this is the product. So you can all write JKL, B and W, NaOH, and what is W is PCC. And reaction 1, 2, 3, the reaction 1 is this, that is a electrophilic substitution. This is nucleophilic substitution, and this is nucleophilic addition, right? So what is the structure of the major product that is formed between this alkene and HBr? So according to the Markovnikov rule, so there will be one hydrogen here, and the bromine will be here. If it is anti-Markovnikov, these two exchanges. Okay, write the mechanism. So mechanism, we have seen this many times, the many mechanisms of these kind of the questions that is related to this mechanism. So don't forget, always the attack start from the pi bond. So this attacks the dipole, that is HBr. So this is a delta plus, and this is a delta negative. So this bond is going to be broken like this. So this is the first step that will form the carbocation, right? So it will form the carbocation plus Br minus. In the second step, this carbocation, which is here, this is the positive carbon. Typically, it is the CH3, CH3, and hydrogen. And this Br minus here is going to now attack here this and form the final product. That is the major product plus and a minor product, which we don't consider. That is the major product in anti-Markovnikov, right? So in the Markovnikov, this is the major product. This one. So we are done with that. So